basic source estimation. So Pablo, go ahead.
Thank you very much. Can you see my screen?
We can see.
Okay, thank you so much. So this is Pablo de Villeros speaking. I'm a PhD student from CIMBESTAF Guadalajara and UPHF in France. And today I'm going to present part of my work during my PhD titled Distributed Predefined Time Optimization for Basic Source Estimation. So multi-agent systems is a very trendy topic in control engineering at this moment due to the advancements in digital systems, communications, and sensing devices. In this context, an agent can be considered as an intelligent entity which has decision-making capabilities, and all the agents in the system interact to pursue a particular common objective. If this objective is concerned with the minimization of local functions that are private to each agent, we are talking about distributed optimization. This approach has been used in many applications. For example, for smart grids, in machine learning, social networks, and very recently for AGVs and robotic systems in general. Okay, now some preliminaries to understand what we were working on. So imagine you have a suitable Lyapunov function for the system, and then depending on the convergence of the equilibrium, we can classify this convergence in three types. The first one is asymptotic convergence, which is the very typical one we use for our analysis. But when time is a hard constraint, this is very inadequate. There's another approach called finite time convergence, in which the upper bound of the settling time is finite, but it depends on the initial conditions. Finally, we have fixed time convergence, in which the upper bound of the settling time is independent of the initial conditions. But the relationship between this upper bound and the parameters of the system is not explicit. It's not explicit enough. So there's a new approach called predefined time, which is an enhancement to this fixed time convergence, in which the upper bound of the settling time is a user-defined parameter, meaning that we can establish an upper bound in advance. Okay, about graph theory, some of you have spoken about this, so I'm going to be very quick. Let's say we have a graph chi that is composed of nodes or vertices, or in this case, agents. The connection between these nodes is called edges, and these edges are represented by a square matrix that we call adjacency matrix. An undirected connected graph is, we have an undirected connected graph is if all edges are bidirectional, and if there exists at least one path between any two vertices. Another way of expressing the connection between agents is the Laplacian matrix. Some of you have talked about that. It's defined as you may see on the left. On the right hand of your screen, you may see a very simple example where we have four agents. That graph is undirected and connected, and we have the adjacency matrix and the Laplacian matrix. When we have undirected connected graphs, this Laplacian matrix is symmetric. The first eigenvalue, as someone mentioned before, is 0. And the second smallest eigenvalue, which in some texts is called Fiedler eigenvalue, is directly related to the connectivity of the network. Finally, about convex analysis, we have a twice differentiable function, and we consider it strongly convex if it holds those two conditions. if this function is strongly convex, we can guarantee that there's a unique optimum. Analogously, if a twice differentiable function is smooth, theta smooth, we can guarantee that its gradient and Hessian is Lipschitz continuous. So pay attention to these two concepts because I will talk about them later. Now let's move to the problem formulation. Imagine you deploy some sensors around a particular area, and there are some agents in the surroundings. Now, there's a source of a particular kind, let's say a noise source or a pollution source, heat source, etc. And we're going to consider it isotropic. Some of the sensors that were deployed in the area get active, and after that, they send information to the agents. The agents communicate among them, not all of them, but with their neighbors. And with that information, they move to the estimated location of the source. I want to emphasize that this is the estimated location of the source, because depending on the position of the sensors and the connection between sensors and agents, it could be a little deviated, but maybe the agents have some onboard sensors that are capable to bring them to the precise location of the source. So this is just an approximation. We can translate that in a mathematical form. Let's consider a first order system. The agents have a first order dynamics. And the idea is to minimize, as I told you before, the sum of the local functions. And we define the local functions, as you may see here. It's a quadratic form in which we have the difference or the distance between the position of the agent and the position of this activated or active sensors connected to the particular agent. As you saw before, maybe an agent has the possibility to connect to several sensors. So we have here a parameter dik that is 1 if the agent I has access to the sensor k, or 0 otherwise. Now the constraint. The constraint is concerned with the convergence to the global minimum. And under this structure, the global minimum is the estimated location of the source. So the idea is that the agents converge or perform consensus to that point in a time less than Tc. Tc is the upper bound of the settling time. Now, if we may want agents to adopt a particular formation, so we can change that position to a displacement just by introducing this pi, which is the state of the agent, minus a fixed offset that is established by the user. In this way, agents can adopt a formation around that estimated location of the source. We need two assumptions. The first one, of course, the communication topology is described by a fixed, connected, undirected graph. And the second assumption is that the local functions are twice differentiable, small theta strongly convex, and big theta smooth. And as you may see, this is a quadratic function, so it meets both conditions. Here are the results. Is the algorithm we developed. It's a two-step algorithm. Allow me to start explaining the second part of the algorithm. As you may see, we have here a sum over the neighbors on the network. So this second part of the algorithm is concerned to bringing the agents to the global minimum. This symbol here is the vectorial signum function. So why do we need a first step, a prior step? Our algorithm is based on the zero gradient sum theory, for those of you who knows it. And in order to work, the agents must start at their local minimums, which is a very restrictive condition, and it's impractical. So we have to add a first step in which every agent individually goes to their local minimum, and from there they perform communication, they start communicating themselves and perform consensus or formation. The rest are just constants, but I want to bring attention to this last constant, C3. C3, it depends on the theta bar. This theta bar is the maximum among all the smooth parameters, and lambda 2, which I explained before. So as long as the C3 parameter is higher than or equal to this fraction, we can guarantee that the agents will converge in predefined time TC. One last thing, since we have two steps, we introduce this parameter mu, which is just to establish the duration of either phase or either step. So it goes from 0 to 1. Okay. The proof of stability is quite long, so I invite you all to read our paper later. But I want to talk very briefly about the Lyapunov functions we used for this algorithm. For the first step, we used a pretty common Lyapunov function, which is the square norm of the gradient, which is positive, radially unbounded, and equal to 0 if and only if the gradient is 0, meaning that the agents achieve their local minimum, right? But look at the right-hand side equation. This is quite uncommon, at least for most of us. It's not the typical Lyapunov function, but if you remember, we saw earlier an expression for strongly convex functions. So this is pretty similar. And we can guarantee that this Lyapunov function is a suitable Lyapunov function because it is positive, it is radially unbounded, and it's equal to 0 if and only if the displacement of every agent is equal to the global minimum. Okay, here goes the simulations. We have, for this example, 5 agents with first order dynamics, I insist. According to this topology, the lambda 2 parameter is 0.38. And we have this accessibility matrix, which says the sensors which are connected to the agents. For example, the first row says that agent 1 is connected to sensor 1 and sensor 2. The last row says that agent 5 is connected to sensor 4, etc. So on the left, we have pure consensus. So we establish the displacement, the offset equal to 0, and we establish a predefined time 40. So let's see. So the agents first visit the local minimum, and then they go and perform consensus to the estimated global minimum in less than 40 seconds or 40 units of time to be precise. On the right, we apply a displacement for every agent. So they will adopt a formation, a pentagon, embedded in a circle of radius 0.4. Let's see how it goes. So they first visit their local minimum, and then they adopt the formation around the estimated location of the source in less than 40 units of time. These are 2D plots, but it's pretty much the same thing. On the top of your screen, you see the 3 coordinates because it's 3 coordinates, but in terms of the time. So you may see that agents first go to the local minimum, and then they perform consensus to the global minimum in less than 40 units of time. And the last figure shows the behavior of the control input, the norm of the control input. Okay, so conclusions and future work. So our proposed algorithm can be used for both formation and consensus control. The optimization time can be assigned arbitrarily. And this third conclusion is very important. Agents do not need to share the local functions or gradients or Hessians. So it is indeed a distributed scheme. And this will contribute to the reduction of the communication burden and preserve privacy. For future work, we are planning on relaxing the strongly convex condition, applying event triggering control to include equality and inequality constraints, and the applicability on directed graphs. So this is it. Thank you very much for your attention. And if you have questions, I'm pleased to answer all of them.
Thank you, Pablo, for your presentation. So we have time for questions. Someone has a question in the room. Please express. It's time for questions. Go ahead.
Don't be shy.
In a practical situation, what is the control, the input control?
Yeah, let me show you again. You still can see my...
Yeah, I can see.
Let me go back. This is it. It's a two-step control input.
Yeah, and in a practical situation, that means in a physics equipment, I don't know, the physics, what is the input control? Is an electrical signal, what?
Okay. Since we are talking about consensus in a multi-agent systems, there's communication among the agents. This is this Pij parameter here, which is just the difference between the displacement on every agent. So the agent must share information concerning their position. And with that information and the dynamics, the internal dynamics of the agents, they move collaboratively towards the global minimum.
Okay, thank you. Felipe, go ahead.
Thank you for your presentation. In this sense of practical scenario, what would happen if the source presents noise?
Presents what? Sorry.
A kind of noise. If you
Okay. Yeah. For this work, we established that the source must be isotropic. But in the case of noise, we have another work in which the agents are robust against match disturbances. But we're still working on that. It's not that simple. So for this case, we just simplify this approach, saying that there's no noise and the source is isotropic. That's why we say basic source estimation, because you may have many variables here. It's not a very simple problem, but we try to address it step by step.
Thank you.
Thanks for your question.
Okay, thank you very much again. So it's time to move for the next presentation, and I think this is for Felipe Ramirez with the work